So I've spent many years first aspiring to be a scientist from the age of about 5 years old, and then ultimately worked my way through many different colleges and many years in school until ultimately I think I can claim that I have been a scientist now for, I don't know, probably since about somewhere in the 1980s. And one of the things that was really impressed on me was the scientific method and how powerful and important that method is in helping us to distinguish truth from things which have some appearance of truth but may not be. And so I wanted to discuss this morning a trend, a sort of a discouraging trend actually that I'm seeing in science, and if things keep going in this direction, I'm afraid that we could be in the place where really science is no longer a valuable tool. And so so I want to talk about that just a little bit. It's interesting that here we are in a creation seminar, and one of the best pieces of looking for the evidence of creation, just the powerful fingerprint of God, is to use one of the most powerful things that science has done, the Hubble Space Telescope, which is an incredible, complex instrument that has taken really our entire history to put together. And yet, every time we look in any direction with that, what does we see is millions of galaxies. And this is not a picture of stars. These are pictures of galaxies that every one of these things. And so I thought this was an interesting backdrop to the discussion of science overall. So I'm going to put it actually in the background, and that will be the backdrop for this. So this is my outline. I'm going to start with just the definition, talk about the scientific method, and then I'm going to talk about something called pseudoscience and see if we can help distinguish some things. And then I'll go through a couple of different examples of things, and then we'll wrap it up. So the definition of science, it comes from the Latin word scientia. It just means knowledge. It's attained through the study or practice covering general truths, operation of general laws. It's obtained through the scientific method. The purpose of science is to produce useful models of reality. It's to help us understand what is happening in the real world, what it really is. Again, it's a search for truth, I think. It's described for us in the Bible. We have in some ways, the scientific method described for us right in the Bible. For the invisible things of him, since the creation of the world, are clearly seen, being perceived through the things that are made, even his everlasting power and divinity, that they may be without excuse. So it tells us in the Bible that we will find his fingerprint in all of creation. It's interesting, the next verse cautions those that know God and know of God and then ignore him. Because they, knowing God, glorified him not as God, neither gave thanks, but became vain in their reasonings, and their senseless hearts were darkened. Professing themselves to be wise, they became fools. And I'm afraid this is all too true of many of the people these days which call themselves scientists, and many of my peers that I rub elbows with on a daily basis. I see them drawing very good scientific conclusions when they have evidence in front, but then they turn into a blind side when it comes to certain areas. And they fall into the trap of some of the pseudoscience, which we're going to talk about. The scientific method is actually very simple. It's just observation and research. You look at things in the world around you in any particular field of study. You form some form of hypothesis, and then with that hypothesis you make a prediction. And the prediction has got to have a couple of criteria. It has to be falsifiable. It has to be something that can be true or not true. And then you have to do an experiment, and you validate that your prediction came true or not. And then from that you can form a conclusion. And of course, if it wasn't validated, you have to change your hypothesis, and then start the cycle again. So you have to make objective observations. You don't want to make subjective observations that, based on speculation, based on the way you want things to happen. Your specific predictions have to be testable. It has to be something that you can actually test, and it has to be falsifiable. It has to be something that can have a false answer. Then you have to find a way to perform experiments. Now, performing experiments isn't necessarily just playing with your chemistry set. It may actually be observational experiments. You may make a prediction that all of the galaxies, the further they are redshifted by a certain amount. And so you base that on some observations. And then when you find new galaxies, you say, does that new fact, does that new experiment fit my theory, fit my hypothesis? And if it doesn't, then you have to highlight that as well. You can't throw out that data that you don't like. You have to keep all of the data. And then validating the results is really an important part of it. You have to go back and say, okay, here was my prediction. How did I do? How did I do against that? And if it's not right, you have to provide something that's supported by the evidence. So validation is an important concept in science. We make scientific instruments for measuring the eye, and I've been doing a lot of research in measuring the eye. And one of the key criteria for that is the instrument that you've made an instrument that's actually useful to the clinician to really be able to measure your eye. Can it really measure an eye? And does it give you the right answer? Is it accurate? Is it predictable? Is it repeatable? Can that information then be used in order to do something useful? In our case, we make instruments that measure the eye for used in laser refractive surgery, which is commonly called LASIK or PRK. And so we have to follow that whole step and actually follow it all the way through to the end user. Make sure that what we've built is valid. It has good validation. So we have to compare that. And so it's a useful term in many fields. So here's an example of a prediction. So in 1954, a group of engineers, budding computer scientists, although I don't think computer science existed even yet, they made a model, a prediction of what a home computer would look like. And so here's their prediction. So I think the caption is really interesting too. It says it would require yet not invented technologies, and it would be easy to use with a teletype interface and the Fortran language. So here was a prediction, and it's the budding field of computer science, and so this in a sense is a scientific prediction. So let's do the validation. Of course, we know that they were a little bit conservative in their predictions. And so now I think there's the typical count for computers in a home is somewhere between 15 and 20, because every thermostat, every clock, every one of those little pieces that you have really has a computer in it. In fact, it's an interesting fact. There's these little birthday cards that you can buy, and you open it up, and it plays the tune, "Happy Birthday to You." Well, that little card has a little tiny computer in it. And that computer has more memory, more computer horsepower than all of the computers that were ever built, put together until 1971. So we just take it for granted that we have that this computer technology at our fingertips in every single direction, et cetera. When preparing this talk, I did a lot of it on airplanes. I was stuck because I didn't have the internet. How could I live without the internet? So we take all this really very much for granted. But nevertheless, here's a good example of the validation. What somebody predicted, we have to go back and look and say, well, how did they do? And obviously, it's really hard to predict the future, especially when it's that kind of thing. And I think we'll see some examples in some of the fields that we're talking about today, where people are talking about the prediction and the model, but they're treating it as if that was the fact. We need to focus on what the results are and what the facts are, and not on the models. And this is why this is my concern. This is why I'm calling this the end of science, because it seems like in the popular press and in some of the government agencies and there's a strong tendency for people to focus on the model and not on the evidence. Okay, so what's pseudoscience? So pseudoscience is a methodology of belief or practice where it appears to be scientific, but it doesn't actually adhere to scientific methodology. It may lack supporting evidence or plausibility, or it may be just speculation that is phrased in scientific terms. It comes from the Greek term, which is a pseudo, which sort of is false or pretending, and of course tied in with the word science. And so if you look online, and you can find this thing called the Skeptic's Dictionary, and it's got an interesting set of tests, and there's 10 of them here, which is pretty long for us to go through. But I'm going to focus on sort of 3 or 4 of them, and see if we can take some of the current topics, some of the current sort of hot topics, as John alluded to, and let's just analyze these in these terms. I'm going to start with evolution, and then we'll look at intelligent design a little bit, and then global warming. So, I mean, here's some of the tests that you can use in evaluating something pseudoscience or science. Some things can't be tested because they're consistent with every imaginable state of affairs in the empirical world, or they're so vague and malleable that anything relevant can be shoehorned to fit the theory. So if you find some new fact, then if it's just a speculative theory, you can find a way to explain that new fact in terms of the theory, or you can just change the theory as it goes. And so this isn't really the scientific method. The scientific method does allow for adjusting your hypothesis. But really you have to do that after you've done the validation. You're saying, well, this did not fit the theory, it's false. Let's go back and adjust. Another one of the tests, some pseudoscientific theories are supported mainly by selective use of anecdotes, intuition, examples of confirming instances. So if you take specific facts that you pull out by ones, and you pull out specifically the ones that fit your theory, and you omit all of the ones that don't fit your theory, then you can draw some nice graphs and gather some nice data, and boy, you'll convince yourself maybe that your theory is valid. But really, you're lying to yourself at least. And I always like to say one of the best lies is almost the truth. And boy, it's one of those lies of omission, I think, sometimes are some of the worst ones. And then the last one here, pseudoscientists claim to base their theories on empirical evidence, and they may even use some scientific methods, although often their understanding of a controlled experiment is inadequate. So we'll look at sort of these three things. And so we'll start with evolution. Of course, this, evolution, I think, probably started out as a roughly scientific theory. It started out with observations of a fossil record and change of species, the great variety of species. And so that led to this theory by Charles Darwin that random mutations actually, he was not so specific about it being mutations. He talked about changes in the protoplasm. At the time, they didn't even have a microscope good enough to see the cell. So they didn't really know what was in there. So, but he described very carefully this idea of natural selection. And so out of that, there comes a set of natural predictions that you